Standard Java exception handling often hides a catastrophic performance trap. What looks like clean programming can leave your production hardware glowing red hot. In many enterprise systems, mid-level developers rely on exceptions to handle routine business logic, such as throwing a user not found exception simply to signal a missing search result. Under heavy production traffic, this practice saturates CPU cores and slows the application to a crawl. Without an understanding of native JVM assembly mechanics, a system will encounter cascading timeouts and fail container restarts, even when the logic itself is technically correct. This hidden tax mirrors the order key challenge. When 50,000 identical hash codes map to one array bucket, it overflows. Exceeding 8 entries, the JVM mutates this into a red-black tree. To navigate, it searches for a comparable interface for left-right routing. Since OrderKey does not implement comparable, the map relies on secondary tiebreakers. Because these provide no unique direction, the JVM is forced into an intensive traversal loop down every branch. Lookup performance settles into a linear O of n scan, saturating the CPU. This demonstrates how ignoring underlying JVM behavior creates massive architectural debt. Maintaining system stability starts with the java.lang.throwable hierarchy. This tree determines how compile-time syntax boundaries interface with the runtime. The error branch represents catastrophic system-level failures, typically resulting from JVM infrastructure exhaustion. Application code should never attempt to catch or recover from an error. At this point, the runtime environment is no longer stable or predictable. Program-level anomalies fall under the exception branch, which the JVM handles differently depending on the subclass. Checked exceptions enforce compile time constraints, requiring an explicit try-catch or throws declaration. These are intended for foreseeable, recoverable environmental failures. Unchecked exceptions, or runtime exceptions, represent logical flaws or API misuse. These require clean code corrections rather than tactical recovery wrappers. When these categories are treated as mere syntax rules rather than architectural boundaries, system instability is the inevitable result. The CPU spikes associated with exception handling are driven by a specific mandatory native JVM method call embedded in the Throwable constructor. That method is public synchronized throwable fillInStackTrace. Instantiating an exception triggers this call, which halts execution to take a full physical snapshot of the current thread stack. The JVM loops backward through every active frame, capturing the class name, method name, file name, and line number for every layer of the stack. In frameworks like Spring Boot, stack depths regularly exceed 100 frames due to proxy interceptions. This scanner illustrates the heavy CPU cost of extracting data from every single one of those layers. This massive stack walk pollutes the execution pipeline, turning routine business logic into a major performance bottleneck. To solve this, A3 senior engineers design high-performance, lightweight business exceptions for internal signaling. By overriding fillInStackTrace to instantly return this, as shown on the right, you disable the stack walk entirely. This optimization makes exception instantiation nearly as fast as creating a standard data transfer object. We see the same attention to detail in resource management, specifically with the auto-closable contract and try with resources. Before Java 7, closing OS-level descriptors required nested try-catch finally blocks that frequently dropped or obscured underlying errors. A conflict arises if the business logic throws an error, and the subsequent resource closure also fails. Since a Java method can only propagate one exception up the stack, these two failures must be reconciled. In legacy code, the finally block would overwrite the primary business exception, masking the root cause of the crash. Modern bytecode deconstruction reveals how Java now preserves the primary error while capturing the secondary failure. The secondary exception is appended to the primary mechanism ensures that operations teams never lose the diagnostic data needed to identify a root cause. Applying these insights requires a senior-level review of code smells that threaten production stability. Hazard 1 is swallowing exceptions. Leaving a catch block empty erases the error signal entirely. This leaves operations teams blind to bugs and allows state corruption to propagate. Hazard 2 is the log and throw pattern. Logging an error and immediately rethrowing it causes chaotic log pollution, duplicating stack traces in your aggregation pools for every layer the exception traverses. Hazard 3 is catching the base throwable interface. This inadvertently traps fatal infrastructure safeguards like out-of-memory error. Trapping these failures prevents the JVM from shutting down cleanly, often causing stalling containers that cannot restart. Robust architecture isn't built at the syntax level. It's built by understanding the massive, blinking infrastructure that executes your code. Production stability requires moving past textbook assumptions and mastering the exact runtime behaviors of the JVM.